All right, everybody, let's get started with the last session of the day. My name is Raymond Nason from Electronics. I'll be the chair of this session, which is about architecture, CAD, and circuit design. We've got 5 presentations in this session, so we will spend some time before the banquet starts in the evening. Like Giro said in the beginning, make sure that when you leave the room, you don't leave any laptops or anything else behind, because this room will be rearranged. The first paper of this session is going to be presented by Stefan Nikolić. Stefan obtained his bachelor degree in electronics from the University of Novi Sad in Serbia in 2017. And then started his PhD at EPFL under the supervision of Professor Paolo Ienne later that year. His main research interests are FPGA architecture and associated CAD algorithms. Stefan?
Hear me? Okay, so to begin with, just to make sure that we're all on the same page, I'll quickly go through what we mean by switch blocks. So here we can see how an FPGA typically looks like. So there are these clusters of lookup tables arranged in a 2D grid, and they're surrounded by channels of prefabricated wires. At the input of each wire, there is a multiplexer that is driving it that takes some of the inputs from the lookup tables and the remaining ones from the other channel wires. And when there is a wire A giving an input to the multiplexer driving the wire B, we say that there is a switch between A and B. And this we signify by the corresponding line between the 2 wires. And then the collection of all the switches at the intersection of 2 channels is what we call a switch block. What's important to note is that usually all of the switch blocks are identical. So if there is this switch in one, it will also exist in all the others. And then our task in this presentation is to determine which switches should be in the switch block. And this we should do in order to guarantee that the switch block can route many connections of many different circuits with a minimal delay. So one idea could be, if we assume that delay is usually correlated with the number of hops through the multiplexer that one needs to take, that we can do it fully connected, and then we guarantee the minimal hops and we're done. But of course, this would increase dramatically the size of the multiplexers, so it's not really something that we want to do. And instead, and that would in turn increase the delay of 1 hop. So instead, what we want to do is to make something that is sparse, but can still minimize the number of hops that are taken for connections. And also additionally, it can allow paths implementing different signals not to intersect, which is something that we call congestion resolution. So to sum up, what we need to do is to make this fully connected thing sparse and also regular, which we will define shortly. But before we proceed with the remainder of the presentation, I suppose many of you may wonder whether we are not trying to solve something that has already been solved a long time ago. So if we open some of the recent academic papers, we'll probably see one of these famous switch block designs that have been shown to work quite well time and again. However, if we look at one of the more recent commercial architectures that is implemented in one of the scale technologies, we can see that because of the technological changes, there are some quite substantial changes in pattern design that are also necessary to reap up the benefits of moving to a new node. So ideally, we would want to be able to automatically design switch blocks for a given technology that would be optimized in them. And this is actually not a new idea, so it has been done before. But one of the main problems of the methods that were developed for tackling this problem is that they produce switch patterns that are quite irregular compared to their commercial counterparts. This is some approximate adjacency where we can see this. And now what we're going to do in the presentation actually is that assuming that this regularity that we observe in commercial architectures is needed for layout reasons or maybe for CAD tools, we will first ask how we can extend the ultimate exploration methods so that they always land on regular solutions exclusively. And then we would like to see what is the impact of enforcing regularity as opposed to not enforcing one. So the remainder of the presentation will look as follows. I'll quickly give a review of the LLM search method, which is our previous work on which we built this one. Then I will explain how we extend it to enforce regular solutions. And finally, I will present a few sets of experimental results that apply this method. So before we begin with the review, maybe there is something interesting that you haven't thought about much before, and that is that the way in which the router routes a circuit on an FPGA is actually quite similar to the way in which an artist creates a mosaic. So first, the artist has many different kinds of stone available to create their design. And similarly, the router has many different kinds of switches available. In every square of the carrier grid, the artist can use any of the available kinds of stone. And similarly, the router can use in any switch block any of the available switches to route the connections of the circuit. And then what's more interesting is that there is a similar analogy between the FPGA architect and the seller of the mosaic stones. So the FPGA architect faces the problem of having too many switches, meaning that the pattern is going to be too expensive and too slow. And similarly, the seller of mosaic stones finds it very difficult to serve a customer who requests too many different kinds of stone. What the FPGA architect wants to do is to minimize the number of switches while still making the router happy so that it can route circuits fast. And similarly, the mosaic stone seller wants to minimize the number of different stones while making the artist happy so that they can design nice mosaics. And as you can imagine, the sellers of mosaic stones existed centuries before FPGA architects, so it's foreseeable that they solved some of the problems that we are facing a long time ago. So here we'll meet Ahmed, who was a 16th century mosaic artist, and this is his ideal design of a mosaic containing 1,000 different kinds of stones. And then he sailed to Constantinople to buy them, so he went to Bazaar, and he presented his specification to Mustafa, the shop owner. So the specification holds all the different kinds of stones that were used in a decreasing order of the number of pieces of each kind that were needed to achieve his ideal design. And then when Mustafa saw this, because he has very limited space for storage of different stones, he keeps them in this big pile of different bags. He was not really happy to see this because it would be too much work to move all these bags and serve the customer. But he still wanted Ahmed to be happy, so he thought of this idea that could actually make it a good solution for both of them. So he went through Ahmed's list, and he saw that there are these 10 first kinds of stone that he wants the most. They are the most used in his design. And then he decided to offer him a big discount on any number of pieces of stones from precisely these 10 kinds. But the idea was that if he pledged to remove these 10 bags from the pile, then Ahmed would have to buy. So there is no turning back. And so if Ahmed were to agree, he could go home to redesign his mosaic in order to maximize the number of pieces used of these discounted stones so as to make the whole design cheaper. So Ahmed agreed, and he went back home to redesign his mosaic. And then now let's return to the present moment and see how this applies to our problem here. So we have the initial situation where at the top we see all the switches that are marked for fabrication. So they are going to the foundry, and initially there are none. And then at the bottom, we see all the kinds of switches that the router could potentially use to route the circuit, and everything that we could potentially fabricate is in that group. So what do we do? Well, similarly to Ahmed, we first let Pathfinder route the relevant circuits. And what's important to note here is that every connection is routed with the shortest path through the available resources. Then after that, we simply go through all the switch blocks and count in how many switch blocks the particular kind of switch was used, and assemble a list very similar to Ahmed's specification, so sorted in decreasing order of usage. And then we learn from Mustafa what we have to do. So we pick, for instance, the first two, and we say that these are going to be fabricated and hence are available to the router for free in the next iteration. This we'll see here. So the upper picture increased by 2 switches. And then in the next iteration, Pathfinder will adjust the paths to profit from the discount of the switches, and it will reduce the overall cost of routing. However, although we can see here that some of the switches that were previously used are no longer used because they're no longer preferable when the discount is there, there are some new ones that now became necessary to be used, either for connectivity or congestion or critical path, doesn't matter. So we're still not done. What do we have to do? Well, let's see what happened with Mustafa and Ahmed again. So when Ahmed went home, he managed to reduce the number of stones used to 493 without really reducing the beauty of his mosaic, so he was happy. And then he went to bargain with Mustafa again to try to get this number of different stones. Mustafa had a headache when he saw the list. So what did he do? Well, he said, okay, I'm going to give you a discount for the next 10. Just okay, the same whole story, do the next 10. And then Ahmed went again, so he redesigned a little bit more, bargained a little bit more. And eventually he was happy with the design and all the discounts that he managed to obtain. And by that time, Mustafa had to take out 87 bags, which is much less than 1,000. So still some work, but much less than 1,000. So what do? Well, the same as Mustafa. So we give the discount for the next 2 switches. let the router route with these 4, and now everybody's happy. The search converged, so we managed to route the circuits with only those switches that are marked for fabrication. This is the final pattern that we have. And in fact, this is the algorithm that we proposed in our previous work, which we call avalanche search. So first, the switches that are marked for fabrication is an empty set. And all the other switches, actually everything that we can potentially fabricate, is given to the router at the cost C. And then we iteratively let the router run. And if it uses no more switches that are not marked for fabrication, it means that we converged, so we stop. Otherwise, we simply go through the list of the available switches, and the ones that are used the most, we pick the top 10, mark them for fabrication, then set the cost to 0 for the subsequent iterations. So that's it. But the problem with this is that this is precisely how we get the irregular patterns that we saw before. And in turn, the problem with that is that even if we manage to minimize the pattern size to some n switches, a certain M will be easy to lay out, whereas another M will be very hard or even impossible to lay out. So the real question that we ask ourselves in this presentation is, how do we find M switches that are as close as possible to what the router ideally wants, but that are easy to lay out at the same time? How do we achieve that? Well, fortunately, Mustafa had a similar problem 5 centuries ago, so we can still learn something from him. So even though he pledged to remove only 87 bags from his pile, in fact, he had to move 492 because these 87 were buried within the pile. He was not taking care of where was their position. And this was really too hard for him to do, so he was operating at a loss. And then he asked himself how he could be smarter next time. So how he could give Ahmed 87 kinds of stone that are as close as possible to the ones that he really wants, but in such a way that he never moves more than 150 bags, which was for him the maximum that he could do at the pro. And 2 years later, Ahmed came again to Constantinople, but Mustafa was smarter this time. So when he received the specification from Ahmed, he didn't give discounts from the top consecutively, but he first went through the list from the top, so trying to maximize the values, and he ticked those bags that are in such position in his pile that he was sure, 87 of such, that he was sure that he was never going to move more than 150. So it satisfies his constraints. And then from the top of this ticked list, so skipping some that Ahmed actually wanted, he picked the n most wanted ones. And again, he decided to give a discount to Ahmed at the same conditions. So if he pledged to remove them, they will never be returned back. And in order to guarantee that the constraints are always met, Mustafa made sure that the bargaining always ends at a complete ticked list. So there is one important takeaway from here, and this is that the actual constraints that Mustafa applies depend on the layout of his pile. And this is different for every merchant, but the algorithm is always the same, hence it's also general. So let's see how this looks like for us. Well, the important points are that we can encode almost any regularity constraints that are needed for layout or cat tool reasons as constraints of an integer linear program. And then we simply let the ILP solver maximize the desirability towards certain switches expressed by the router previously, while satisfying the above constraints. The cost update is the same as before almost. So we give a big discount to the n most used unmarked switches that are part of the ILP solution, hence known not to violate the constraints that we set beforehand. And then for the remaining switches that are not part of the ILP solution, but actually violate the constraints, we leave them at the full cost and they're hence expensive. In order to guarantee that the constraints are eventually met, we make sure that the final pattern is the last solution of the last formulated ILP. If we integrate this in the previous avalanche search algorithm, it's almost the same. So the main difference is at the point 5, where we solve the ILP, as we said before, so maximizing the usage while respecting the constraints. And we always retain, of course, the switches that have already been marked for fabrication. Then when we give discounts, as we said, we give them to the n most used switches that are part of the ILP solution itself. Finally, we return when we expanded the number of iterations that we set before. And I will quickly present a few sets of results with this. So first, a little bit on the experimental setup. So we created this architecture that was inspired by Agilex and is hence plane-based. It has 8 6-input lookup tables in the cluster. We fixed one channel composition that was also derived from the one reported for Agilex. All the experiments are done in 4-nanometer predictive technology. In the exploration itself, we used 3 MCNC circuits routed simultaneously with VTR8. And then the remaining MCNC circuits were used for measuring the critical path delay. And we used some a little bit larger synthetic GNL circuits for measuring routability. The first form of regularity that we want to explore is how do we make sure that there are not more than a certain number and different fan-ins and fan-out sizes. And this makes sense because the fewer different multiplexes we have to lay out, the easier the layout will be. And also this is something that we can observe in commercial architectures. So here are first the results for the critical path delay. So each point represents one geomean critical path delay over all used circuits for one particular solution architecture. And in order to increase the robustness, we actually, for each set of constraints, we generated 5 different solutions by permuting the order in which the nets are routed with 5 different seeds. And what we can see here is that the most performant architectures are the ones that are allowed to be irregular. So this is second from the right. But if we make sure that the pattern is actually as large as the one where all the fan-outs and fan-ins are the same, the most of the performance benefit is lost. So what we can conclude is that regularization of fan-in fan-out sizes doesn't really, actually only slightly deteriorates performance, so not too much. In terms of routability, here we have 1 point per one GNL circuit and one solution. And the y-axis is the number of ripped up and rerouted connections over all iterations of Pathfinder. And what we can see is that the irregular architectures actually fail to route most of the circuits. So the regularization of fan-ins and fan-outs improves routability by a fair margin. The second kind that we are going to see here is enforcing that every multiplexer shares at least a certain number of inputs with another multiplexer in the pattern. And this has been shown to reduce the via stacks, the capacitance, and to also reduce area through sharing of diffusion. And here we fix all the fan-outs and fan-ins to be of size 6, and then we sweep the sharing between 0 and 5. We can see that as we increase the amount of sharing, there is a slight increase in performance. And what's important to note here is that we are not able to model the reduction in area and stacks, only in capacitance. So the actual benefits are probably better. And similarly for routability, we can see that it doesn't deteriorate routability. So summing these two up, it means that this is a beneficial technique to do. More forms of regularity are shown in the paper. And as we have seen, almost arbitrary forms of regularity can be enforced in the ILP, in the algorithm. And with this, I come to the conclusion, which is that we developed an algorithm that can respect arbitrary forms of regularity encodable as the ILP. And we also showed that enforcing regularity that is necessary for layout can sometimes even benefit both performance and routability, and it typically doesn't significantly hurt either of the two metrics. Thank you for your attention, and all the source code is available here. There is there.
Hi, thank you for the very interesting talk. So we had one work on, the HARP FPGA, the hardwired back in 2005 and so on. One issue that we saw there was there's a chicken and egg problem with the behavior of the router and the kinds of connections that it wants you to have. But once you change the architecture, maybe the router wants to do things differently. So did you look into co-designing the router architecture, and not necessarily in terms of Pathfinder? If you ask it to do one route, that's okay, but the rip up and reroute and the preference it would give to things. So did you look into that? So that's my first question: router and architecture co-design. Maybe you want to answer that, and if there's time, I'll ask.
Yes, okay. Yeah, thank you for the question. I think this is really interesting. So I think that we cover this in part by doing things a little bit differently than what we saw other people do before. And this is presenting the router with all the switches that are available at all times. So it's not that we serve it these 3 switches and then it can use one of the 3, but then we serve another 3, then it can use another 3. So it can always choose freely as it wants. And this kind of increases confidence that we can actually let it do what it wants to do. But certainly as we evolve the costs, as something becomes cheaper, it's even what we saw in one of the examples. It will want to use something that it didn't want to use before. So there is this chicken and egg problem. And yeah, it would be interesting to try to see if the algorithm can be changed as well.
And can I ask a second question? So the second question I have is, so you're restricting the switch boxes to have few connections and so on. I understand it, and every switch box has to be the same for layout reasons. But what about providing a lot more flexibility on, let's say, 2 tracks. These 2 tracks can connect to any others. And that's going to increase, fan out and the MUX cost, but
Yes.
it would give you flexibility for nets that are not that critical in terms of timing to be able to route, and then you would get much better routability, maybe reduce the total number of tracks and so on. Have you looked into that?
Yeah, so that's also an interesting question. I can go actually here. Sorry, no, not this one. Here, yeah. So here, what we did, we didn't predetermine like this wire is going to have that and that fan out, and this wire is going to get that and that fan out. We encoded, you can see it in the paper, we encoded the constraints in such a way that over the whole switch pattern, there are no more than 2 or no more than 4 different fan-ins and fan-out sizes. How they're assigned is given to the ILP to decide based on the usage from the router. So technically, maybe this could be done even better way, I don't know, but still, it seems that if it's given to the exploration method to decide, there is not too much difference. So only if you really can allow 10 different sizes, then you get to see a drop in critical path delay. Otherwise, it's pretty comparable.
Thank you. Very interesting work. Thanks.
Thank you.
Nice talk. Thank you. I really enjoyed it. One thing is that you concentrated on very small benchmarks. It actually turns out that the switch box that you want to design, regular or otherwise, is a very strong function of the size of the FPGA that you're building. You would design a different switch box for an FPGA less than 50,000 LUTs compared to an FPGA that's larger than 500,000 LUTs. It's not going to be the same switch box, not the same fan out, not the same set of muxes. Have you looked at that problem?
Yes, so very good question again. So here, what we wanted to do is to develop a method that could be used to automatically design for any sizing principle. However, there is a little bit of scalability issue, which is not in fact in the ILP, what may be presumed, but it's in the avalanche search itself. So routing everything while checking all the statistics and trying to minimize takes a fair bit more time than routing in general. So using very large circuits that take hours to route intrinsically would not be feasible in an academic setting. So that's one thing, but the method itself is general and we should be able to use it for that. And then even for the results that were obtained from the application of the method, I don't think that they would change too much, because in the end, the performance benefits of the irregular architecture were exactly because it was possible to sparsify the pattern further because the circuits were small. If the circuits were much larger, it's foreseeable that the gap would even shrink because it would be less, there would be less possibility to sparsify as more connectivity would be needed to support larger circuits that would have to push through more connections in the same region of the FPGA. I hope this answers the question.
Thank you. It strikes me that this is almost seems like, I hate to say it, it's like a training problem.
Yes.
In that you're finding a solution given a training set. Did you ever use a design that was not in the training set to do the evaluation, or were the evaluations within the training set?
So yes, all of the designs, actually there are 17 designs for the critical path that are used for testing. Only 3 of them were used in the training set.
Okay.
But they're still from the same benchmark set, right? So they're
Thanks for the clarification.
Let's thank the speaker again.